Okay, so, so to begin our discussion about the golden ratio, let's imagine a line segment right here. And this line segment is split up into A and B. So here's the actual line segment, and it's split up into line segments A and B. And we want, so this is going to be A plus B. And we're gonna just see what happens if we say the ratio of A to B, or the longer line to the shorter line, is equal to the sum of the two lines. Well, first of all, let's just say such a ratio exists, and let's call it, I don't know, x. Okay, so x is going to be equal to, and let's just move that up there, x is equal to A over B, which is also equal to A plus B over A. Okay, so let's just take the A plus B over A part. Okay, so let's just put let's see what this is equivalent to. This is going to be equal to A over A plus B over A, right? Just split up the fraction. A over A plus B over A. Now A over B. But notice A over B is equal to x. So instead of putting A over B there, we can get rid of that and just put x. Okay. So we can move that over there. It's going to be, instead of B over A, it's going to be 1 plus 1 over x. Okay? Okay. So that's also a definition. Now, I'm just going to go off on a little aside, and I made the fraction line really long. Okay, so we can put x down there, but hey, notice that x is just equal to 1 plus 1 over x. So we can put down here, right? X is equal to 1 plus 1 over x. But instead of putting x there, hey, x is just 1 plus 1 over x. So we can put that there. And then we could put an x because it's 1 plus 1 over x, but we don't have to put x there. We could just keep doing this, right? X is equal to 1 plus 1 over x. But instead of saying x, we could just keep doing this, right? So this is also a definition of this function, this fraction that we're really interested in. So, but we really want to start calculating this number, right? This x, sorry. The easiest way to do this is to get rid of the fraction, first of all. So let's multiply both sides by x. So the 1 over x times x is just 1. And the left-hand side would be x squared. Now, this is also an interesting function, so let's just observe it again. Let's see. Let's take the square root of both sides. And simplify this, so it's going to be x equals the square root of 1 over x. But, yes, I reversed the order. But, look, x is just equal to the square root of 1 over x, so we can replace that. Here, look. 1 plus 1, so x is equal to the square root of 1 plus, and we don't have to write x there. We can put the square root of 1 plus, right, because that's x. And then instead of writing x there, we could put because x is equal to the square root of 1 plus, and actually we could just keep doing this. That's also cool, because the same way that it could be, the same way that x could be represented as 1 plus 1 over 1 plus 1 over 1 plus 1 over, it can also be represented as the square root of 1 plus the square root of 1 plus the square root of 1 plus, and so on. Okay, so this is a cool number. Okay, so we want to solve this. So let's go back to this equation, x squared equals x plus 1. And I put ax squared plus bx plus c so that we can see that the resemblance between this equation and that equation. Now, it doesn't look that similar right now, so let's rearrange it. Let's subtract x minus 1 from both sides. So that means we get x squared minus x minus 1 equals 0. So this is our quadratic equation. So let's solve it with the quadratic formula. Notice that a is equal to 1, b is equal to negative 1, and so negative b is going to be negative 1 plus, because we don't really want the plus minus because we're solving for a positive value here, the square root of b squared minus 4ac. What's that? B squared is negative 1 squared, which is 1. 4ac is going to be 4 times 1 times negative 1, and all over 2a is going to be 2 times a is 1. A is going to be 1, so 2 times. You can verify that, but yeah, okay. I'm just going to move on. Okay, so let's simplify this a little bit. Let's see, negative 1 is 1, of course. The square root of 1 minus, well, let's see, 4 times 1 times negative 1 is going to be negative 4, right? And let's simplify this. 1 minus negative 4 is going to be 1 plus the square root of positive 5. So we're just going to put brackets so we can divide, right? 1 plus the square root of 5. And then extra curly bracket, and then divided by 2. Right. Okay. Let's press enter. And we get approximately 1.61803398875. So x is going to be equal to 1.61803398875, and so on, because, and we know this is an irrational number because the square root of 5 is an irrational number. And instead of writing x here, we have a symbol for this. This is the golden ratio, 1.61803398875, and so on. You can look up the decimal value. So, yeah, you can look up the decimal value if you want. I'm not going to stop you, but go ahead. Yeah, go ahead. Just, I'm not going to do it. Okay, notice that this is going to be an irrational number because the square root of 5 is involved, right? And square root of 5 is an irrational number. Okay, so, I just want to quickly return to this statement right here. X equals 1 plus 1 over x. Notice that if we subtract 1 from both sides, we get x minus 1 equals 1 over x. Sorry. So x minus 1. What's x minus 1? Well, that's going to be getting rid of the 1, right? So that's going to be 0.618, whatever, right? But that's also equal to 1 over x. So the reciprocal of this number is just equal to x minus 1. That's cool. And you can calculate more, right? So, as a flower, the flower has to put down seeds around it, right? And we're going to mathematically model the flower, right? And so that means you could put down a seed, and then turn a bit, and then put down another seed, and then turn a bit. Now, if you don't, I'm going to represent this as a 0-degree turn. Now, I hope you were not thinking of this when you were thinking of a flower. Right? I'm guessing you were thinking of like a sunflower, like the center of a sunflower has all these neat spirals. So I'm just going to put this as a bad flower. Okay, what if we turn half a turn, or 0.5 of a turn, 50% of a turn, right? Then we're going to put down a seed here, and then we're going to go to the other side, and we're going to just go back and forth, right? I hope you weren't imagining this when you were thinking of a flower either. So we're going to also call this a bad flower. So anyway, let's just do one more example, right? So this was 0.5. What's 0.5? That's going to be 1 over 2, right? So that's why we got 2 spokes, or 2 lines. I'm going to call them spokes. Okay. Lastly, just to make you certain of this fact, let's try 1/3, or 0.333, and so on. As you might guess, we're going to get 3 spokes, right? We're going to turn, right? So, one more example. Let's try 0.1. 0.1 is equal to 1/10, so you might guess that you're going to get 10 spokes. And you're right, you're going to get 10 spokes. Okay, it's not done yet. Okay, anyway, it's much less obvious what would happen if I asked you 3/10. Okay, so what would happen with 3/10? 3/10 is, let's see, so you're gonna plop down a flower, turn 3/10 of a turn, plop down another flower, and this is what that looks like. Plop, 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 and you don't make it all the way, and as you can see, we're just gonna get 10 spokes again. Now, I don't want to keep animating this on Keynote, right? I just want a computer to do this for me. Okay, so what's interesting though is what happens when you change it by a tiny amount. So I'm just gonna go over to an animation here. This is on Scratch. So that number at the top is 0.3168. Right now anyway, that means that it's turning 0.6138 of a turn in at the center before plopping down another flower. Now, as you can see in the center, you can already see that it's really close to 0.333333, right? So the number 3 is already dominating because there's 3 spokes. But let's just watch this animation. Okay, so you're gonna see that it actually does move. Look at the number, it's barely changing, but you can see dramatic differences. And like right when we get to 0.333333, we're gonna get 3 spokes, which is gonna happen right around maybe like right now, and it's gone. After a little bit, replaced by other numbers, right? So that's pretty cool. I would say that's pretty cool. Now, I know you're dying to try this, so I know you really want to watch this. The link will be in the description. Okay, so, of course, I don't want to keep doing this and wait for the number I want, right? So, so what I'm going to do is I'm just going to make a computer do it for me. Okay. So here is the number 1 over pi. It's approximately 0.31830988862 and so on. Right? Since pi is an irrational number, we're just going to get 0.31830988862 and whatever, right? So I want to draw the flower so that it spins exactly this irrational number of times. Now, what do you think will happen? Because we're trying to get a more efficient flower, right? Because 0.1, that was a horrible flower, right? So, and 0.2, 0.2 would just be 1/5, which means you get 5 spokes, which I didn't show you yet, but I should. I didn't. Okay. Anyway, here's 1 over pi. So 1 over pi looks something like this. Now, I want you to notice that this isn't, like, really good, right? This is not really what you were thinking of when you were thinking of flower, right? In the center, as you can see, there's a pattern in the center. There's 3 spokes in the center. Also, if you count the outside spokes, there are exactly 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22 spokes. I don't know if 22 rings a bell with something to do with pi. I'll explain the bell in a second. Ding! So the reason these appear is because pi is really well approximated with numbers, right? Pi is approximately 3. Right, and pi, another good approximation for pi is 22 over 7. 22 over 7, and that's why we see 22 spokes. 22 over 7, you're going to get, let's see, 22 over 7 is approximately 3.1428 and so on. I'm pretty sure anyway. You can pause the video right now, get your calculator, try it out right now. I'm not sure. I'm pretty sure it's 3.1428 and it keeps going. But since this is 1 over pi, we're gonna see all of these are gonna be reciprocal. So this is going to be 1/3, which is why you see 3 spokes in the center. And you're going to get 7 over 22, and that's why you see 22 spokes on the outside. And that's because it's 1 over pi. Now this also proves a really important fact about pi. Pi is not that irrational. That's because it's really well approximated with rational numbers. Okay, so let's try another number. Square root of 2 is probably the next most common number. I'm not sure. Maybe it's E or something. So 1 over the square root of 2 is approximately 0.70710678112, and let's just see it. Okay, so it's looking better than pi. 1 over pi, I mean. But you can still see spokes. Excuse me. So you can still see spokes if you want to count them. There's exactly 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 spokes, and that's because 12 over 17 is a really good approximation for the square root of 2. Okay, I mean 1 over the square root of 2. I mean that 17 over 12 is a really good approximation for the square root of 2. Okay, so all the flowers you've seen so far are horrid flowers, right? So what's the best flower arrangement? You might have already guessed. It's exactly the number of particles in each firework here. No, I'm just kidding. So it's exactly 1.61803398875, aka the golden ratio. Why is that? Because the golden ratio is the most irrational number. Why? Because it's really hard. It's really hard to approximate it with rational numbers. So that's why it's the most irrational number. Now, I know what you're thinking. You really want to see the flower. So let's do 1 over the golden ratio. As you remember, as a really fun fact about the golden ratio, 1 over the golden ratio is exactly the golden ratio minus 1, which is 0.61803398875, and so on. I think there are too many dots there. Anyway, let's see the flower. Okay, so already you can see this is a much better flower arrangement. And you can still see spokes. And if you count them, you're going to get Fibonacci numbers. This is really close to a sunflower. Compare them. Here, look. I'll put them side by side. Look at this. Can you see the resemblance? Well, I certainly can. This is just like the one on the right. Is like the center, right? Of a sunflower. Okay, I'm gonna do, so that was 1. I'm gonna do the next one that's, looks unrelated at the start. It's pretty short, so don't worry. Okay, so let's say you're on a, plane, right? Not like a flying plane, I meant like, coordinate grid plane. And let's say each coordinate point has a tree on it. And I'm just going to draw that like this. So each dot there is a tree. And these are mathematically thin trees. So they don't have any width, they don't have any area, right? If you're looking at it from the top. But you can still see them if you look in the right direction. Okay, so, and this is a coordinate grid that extends off to infinity. I didn't draw that here because I can't. There's too little space on the computer screen. But this is a good way to, so this is a infinite orchard, right? Okay, so let's say you're standing here at the origin, right? And let's say if you look in this direction right there, you're gonna see this first tree here, the 1, 1 tree, right? 1, 1 tree. If you look in this direction, you're gonna see the 1, 2 tree. Now, here's the question: is there a direction you could look and not see any trees? Right? Just remember that this is an infinite grid. Okay, so you can't look like down, right, or left, because that's kind of cheating. Another thing you can't do is look up. No trees there. That one's pretty funny. Okay, so let's draw this one again. This has a slope of 1, so I'm just gonna call that the 1 line. Let's say this one, I'll draw another one. This one goes to the point 2, 5, right? No, 5, 2, sorry. Don't mess those up. So I'm going to call this the 1 line, and I'm going to call this the 2/5 line, because that's the slope, right? So is there a line you could look and not see any trees? Well, there's a line, and since you have to look in a line that is a ratio, right? Actually, there are many lines, but since you have to look in a line that's a ratio, right? It has to be a fraction. There are some lines. Can you guess? So, just pause the video and think about it. Right. So, so one line you could look is a slope of pi, right? Pi is a nice irrational number that is pretty good, right? That's a good irrational number, one of everybody's favorites. This is the slope of pi, and this one, interestingly, you won't see any trees. Here's another one. Here's the line E, right? E is approximately equal to 2.71828182884, and so on. Okay, but let's say you're allergic to if these are apple trees, let's say you're allergic to apple trees, right? And you want to get as far away from a tree, and you want to get out of the forest. I mean, you can't, but let's just say you want to try and travel as far as you can without getting close to a tree. Well, I hate to disappoint you, but you're going to get dangerously close to one of them, or a few of them. But can you guess what line you could use? Well, like I've hinted about, this line is the golden ratio. Golden ratio is, I don't have to remind you, 1.6180338, and so on. And the golden ratio line looks something like this. This is the farthest you'll ever get. I'm pretty sure I didn't draw it right. I'm sure you can do better, but you're gonna get pretty far, pretty close, pretty far from all the trees. Okay, so to recap, you learned how to calculate the golden ratio, learned about the symbol for the golden ratio, learned why flowers always follow the golden ratio, and you learned about infinite orchards, orchards, yes. Okay, so I know you really want to play with the flower animation. To play with the flower animation online, the links are in the description. Thanks for watching. If you like this video, please consider liking and subscribing. Also, share this channel with others. See how to do stuff with Ethan.com. I mean, how to do stuff with Ethan.com. And see you next time. Bye.